Welcome to the sixth lecture in the series of lectures on Galilean laws of motion by DHS Maithripala. This lecture is dedicated to understanding the behavior of free rigid bodies. A free rigid body is a set of particles that are interacting with each other in such a way that the relative distance between any two particles remain constant, and the interaction between these particles and the rest of the universe is so small that it can be neglected. The motion of such a set of particles can be described by this set of equations or by this set of equations equivalent. This set of equations describe the fact that the rate of change of linear momentum of all the particles is zero, and the rate of change of angular momentum of all the particles about the center of mass is zero. Or in other words, the linear momentum of all the particles is conserved, and the angular momentum of all the particles about the center of mass is conserved as viewed in an inertial frame. The equivalent body frame versions tell us that the rate of change of body angular momentum, or the body frame version of the angular momentum, is given by this expression over here, and that the center of mass acceleration of all the particles is zero. We have also seen that the kinetic energy of a rigid body is given by this expression over here in a previous lecture, and that when you get the rate of change of the kinetic energy, you get this expression over here. Since for a free rigid body, the external interactions are so small and can be neglected, this resultant external force is zero, resultant external force moment is zero, and therefore the rate of change of kinetic energy is zero. So in addition to the conservation of linear momentum, conservation of angular momentum, we see that the kinetic energy is also conserved in a free rigid body motion. If you look at the rate of change of the magnitude of the body angular momentum, capital Pi, we find that that is given by this expression over here. Again, since it is a free rigid body, the external interactions are negligibly small. So this is can be assumed to be zero. And therefore, the rate of change of the magnitude of the body angular momentum is also zero. Or in other words, the magnitude of the body angular momentum also remains constant for free rigid body motion. So let me look at this a little more detail by observing that the moment of inertia tensor is symmetric and positive definite. So what does that tell us? What that tells us that the eigenvectors of the moment of inertia tensor are orthonormal to each other. Therefore, we can fix the body frame in such a way that the body frame axis align along the eigenvectors of the moment of inertia tensor. So when you do that, the momentum inertia tensor takes a very particularly simple form of a diagonal form, where the diagonal entries are the principal moments of inertia. In this representation, where the body axes are fixed along the principal moments of direction, so that the inertia tensor is diagonal, this expression that governs the evolution of the body angular momentum takes the following simple form. So this matrix expression becomes this three simple coupled differential equation. So the free rigid body motion is completely described by these equations in the body angular momentum space. So summarizing, we also saw that the spatial angular momentum is conserved. So spatial angular momentum takes the form I omega, where omega is the body angular velocity. So when I is diagonal, it takes this simple form. And when I is diagonal, the kinetic energy can be written down in this fashion. And the magnitude of the spatial angular momentum can be written down in this fashion. So let's look at the consequences of these observations. So the free rigid body motion is described by these differential equations in the body angular momentum space. We find that these three quantities are conserved. There are three entries in this one. So in other words, R times pi1, pi2, pi3, this matrix is constant. And kinetic energy is constant. And the rate of the magnitude of the spatial angular body angular momentum is constant. So what does this tell us? So if you look at the body angular momentum space, the space of capital pi 1, capital pi 2, capital pi 3, the kinetic energy, the constant kinetic energy surface. So if you look at this, this is a surface in the angular momentum space, pi 1, pi 2, pi 3. This equation describes the surface. In particular, it's an ellipsoid. And this also defines a surface, a very simple surface, a sphere. So what does this tell us? We know that the equations of the behavior of the rigid body is governed by this differential equation in terms of body angular momentum components, pi 1, pi 2, pi 3. And that the solutions must ensure that this quantity is constant and that this quantity is constant. So in other words, if you look at the solutions evolving in the body angular momentum space, they must lie along this constant surface, the kinetic energy ellipsoid. Then they must also along this surface, the body angular momentum sphere. So these are two surfaces in a three-dimensional space. They intersect generically in a curve. Therefore, if the solutions must lie on that surface and this surface, what that means is the solutions of this must lie in the intersection of these two surfaces. So that's what I have summarized over here. Solutions of the free rigid body equations evolve on constant energy ellipsoids and constant angular momentum spheres. Since the solutions of the free rigid body equation must lie along the intersection of the kinetic energy ellipsoid and the spatial angular momentum sphere, let's look at these intersections, because these intersections represent the solutions in the angular momentum space, body angular momentum space. So in these two figures, these black grid lines represent the kinetic energy ellipsoid. So we will think of a situation where we try to maintain the kinetic energy at a constant value. We will maintain the kinetic energy at a constant value, but change the angular momentum and see what the corresponding motion looks like in the body angular momentum space. Why? Because then the solutions are given by the intersection curves, and we will see, okay, so we will fix the kinetic energy ellipsoid because the kinetic energy is fixed. And then for different values of the spatial angular momentum, what will the solution curves look like? So let's start by thinking of a situation where the body angular momentum sphere, given by this pink one, is inside this kinetic energy ellipsoid. So if it is not touching, then it cannot be physical, because the solution should lie on both surfaces. So therefore, they must be intersecting. So the first situation that we can consider is the sphere being inside the kinetic energy ellipsoid and touching these points over here. So what does that mean? So the solution should be on the ellipsoid. It should be on the sphere. Where is that point? Well, that is this single point. So the solution corresponds to the body angular momentum staying fixed at that point. Now let's increase the radius of the body angular momentum, or increase the body angular momentum a little bit. What happens? The sphere pops out. The sphere pops out like this one shown in green. So the sphere pops out from inside the ellipsoid, and now it will intersect along a curve like this green curve. So if you increase this thing a little bit, the sphere will pop out and intersect at this. So this is shown by this green sphere that is popping out of that. And therefore the solutions are these intersecting curves. Now if you increase the radius a little further, this radius will increase and come to a point where now it touches this point over here. Now it will be popping out, but it will be intersecting the kinetic energy ellipsoid along these curves and that point over here. Now if you further increase the radius of the angular momentum sphere, you will see that the sphere and the ellipsoid will intersect at a point along a curve like this. If you further increase this, they will come and the sphere will touch the ellipsoid at these points and will correspond to solutions that are given by points in the angular momentum space. So what do we have? If you look at these intersection curves for various different body angular momenta for a constant kinetic energy, so this ellipsoid is fixed. You change this and draw the intersection curves. And these are those intersection curves for various different angular momentum. So this is when the angular momentum sphere is inside the kinetic energy ellipsoid. This is when it is slightly larger and popping out from inside of the kinetic energy ellipsoid. This is these, and these are when the sphere is touching this point and therefore touching all those curves. And this is when the sphere is intersecting the ellipsoid in a manner similar to shown in this pink sphere. And if you increase it further, it will intersect only at a point here where the pink curve now will be barely touching, or touching, just about touching at that point over. So these intersection curves give you the corresponding solutions of the free rigid body, or the corresponding differential equation. So again, so what we see is the solutions of this differential equation must be given by these intersecting curves. And since these intersecting curves are closed curves, what we notice is almost all the solutions of this differential equation gives you periodic motion in the body angular momentum space. So all free rigid body motions, almost all free rigid body motions correspond to periodic motion in the body angular momentum space. That is an easy consequence of this analysis that we have seen so far. And we also see that, well, these are special types of solutions, and that this corresponds to relative equilibrium. This and that corresponds to solutions of this form. So if you plug in this solution in this differential equation, you will see that this satisfies this differential equation. If you plug in this in the differential equation, you will find that this satisfies the differential equation. And if you find this solution in this differential equation, you will find that that satisfies the differential equation. So what are they? This corresponds to this point, this corresponds to that point, and this corresponds to that point. And since when you plug them, the right hand side is equal and they are staying there, you call them equilibria. And we call them relative equilibria because this will correspond to, though it is equilibria in the body angular momentum space, the body is actually spinning about these axes when they are at that point, and therefore they are called relative equilibria. This also shows something very interesting. So if you start close by this equilibrium, since all solutions are these closed curves, the solution stays near them. If you start close to this, it also still stays near it. However, if you start close to this one, immediately you start moving away from this. And therefore, this equilibrium and that equilibrium are stable, but this equilibrium is unstable because you start slightly away from it, you are immediately taken away, and though it comes back, but it moves away from the equilibrium. And therefore, that's an unstable equilibrium. So these two are stable. This and that pi 1 and pi 3 bar are stable equilibria, while pi 2 bar is an unstable equilibrium. Let us demonstrate this a little more clearly using this animation by Vadim. But unfortunately, his notation does not match with mine. So I will first describe what these notations mean. So here, J is I in my notation, and simple omega is capital omega in my notation. So Jx is I1 in my notation. Simple omega x is capital omega 1 in my notation. So this orange surface is the kinetic energy ellipsoid. The blue surface that you will see inside, that you see barely inside, corresponds to the body angular momentum sphere surface. So we will consider the initial case where the kinetic energy is fixed. So we will be, through this entire mental exercise, we will think of the situation the kinetic energy is fixed. So this kinetic energy ellipsoid will be fixed, but we will change the body angular momentum. Therefore, this surface will change. The radius of this sphere will change. So we will first consider the situation where it is barely lying inside. So that is, it is just touching these 2 points. And so what that means is that this is a solution, or in other words, the angular momentum is staying fixed there. So that is what you see over here. Angular momentum is pointing that way, and this is rotating that. So if you increase the radius of this sphere a little bit, that sphere pops out, and now it will intersect along a curve like that, and that is periodic. So if you notice, this arrow is tracing along this curve over here. And if you increase the radius further, if you increase the spatial angular momentum further, you notice that it will now be touching at that point and also along these curves. And the physical behavior is this. So it is spinning about that axis. But notice something funny happens, and it starts moving away. The reason for that is these are numerical simulations, so you can't exactly start here, or these numerical simulations don't ensure the conservation of these quantities. So you are really starting very close to this, and therefore you will move away from that and come back to that again. So that is what you notice in this animation over here. So now let's think of what happens if you increase the body angular momentum a little further. This sphere will increase its radius and now will intersect along somewhere along here. So as you know, see over here. And again, the solutions are periodic in nature because these curves are closed curves, and this is the physical situation that corresponds to that solution. The physical behavior of the rigid body that corresponds to that periodic motion in the angular momentum space. Now, if you increase the radius further, you will come and touch this point, and then the solution is just that point, or in other words, the relative equilibria, and the physical behavior of that motion will be something like this, where it is spinning about that axis. So I invite you guys to carefully look at this, think about what I have said before in the previous slides, and take a very close look at this animation. In this next slide, we have the actual physical implementation of this situation. And this is an experiment done in the International Space Station. And I will leave it for you guys to try to figure out what is happening over here. And explain this using the equations and the description that we did before. And I have given that as an assignment, and also it is in the company lecture notes. Thank you.